Gum arabic was defined in Thorpe's Dictionary of Applied Organic Chemistry as the gummy exudates from acacia trees grown in hot, dry climates. Gum arabic is used to thicken foodstuffs and also pharmaceuticals, and before the bacterial dextrans were used, gum arabic was used as a blood plasma extender. Blood plasma extenders are used to treat patients who are in shock after losing a good deal of blood. According to Thorpe, the most esteemed variety of gum arabic of commerce is a gum obtained from Acacia Senegal, which grows in the Kordofan province of Sudan in North Africa. So when we talk about gum arabic, we really mean Acacia Senegal gum, and sometimes called Kordofan gum. Sullivan and others were interested in the chemistry of gum arabic before 1900, but very little progress was made. Then in 1929, a most unusual paper appeared from Heidelberger, Goebel and Avery, who were working in the Rockefeller Institute in New York. They reported that they'd hydrolyzed gum arabic for a short time with mineral acid, and that an aqueous solution of the degraded gum gave strong reactions with both type 2 and type 3 pneumococcal antisera. Heidelberger's work excited renewed interest in the chemistry of gum arabic. During the early 1930s, Nobel laureate Sir Norman Howard and Edmund Hirst, who were working in the chemistry department of the University of Birmingham, England, became interested in the chemistry of gum arabic. A few years later, Fred Smith joined them, and then significant advances were made. The going was by no means easy, and 20 years later I heard Gerald Aspinall in Edinburgh state that his papers published in the Journal of the London Chemistry Society in 1939 and 1940, Fred Smith described the very finest experimental work ever carried out in organic chemistry, of course up to that time. Even so, I think Gerald Aspinall's statement was a wee bit exaggerated when we think of some of the things that Emil Fischer, Hans Fischer and Reichstein managed to do. But Fred Smith's work was very good indeed. I once remarked to late Professor Fred Smith that it was amazing he did work of that quality before paper chromatography was used in carbohydrate chemistry. All he said was it was very difficult. So now there's a formula of the gum arabic macromolecule as given by Aspinall, Hirst and Nicholson in a paper in the Journal of the London Chemistry Society in 1959. That formula was based on the results of the British school in 1930s and 1940s, on results which Fred Smith and his collaborators obtained in Minnesota in the 1950s, and of course the few results which were obtained in the 1800s and early 1900s. The story I heard was this. In 1942, the British government sent Fred Smith and some other British scientists to Canada to see if they could make an atom bomb. The British scientists collaborated with Americans who were working on the Manhattan Project, and a few atom bombs were made. While he was in Canada, Fred Smith met and married an American woman, and after the Second World War, he became a professor at a university in Minnesota. From the previous formula, it can now be seen that P is D-galactose in the pyranose or six-membered ring form. DGPA equals D-glucuronic acid in the pyranose or six-membered form. Now R can be L-rhamnose in the pyranose form, or it can be L-arabinose in the furanose or five-membered ring form, or it can be a disaccharide where D-galactose is linked to L-arabinose by a 1,3 link, and in the molecule, the L-rhamnose is in the furanose form. Some people may be surprised to see that the individual monosaccharides can be either in the D-stereochemical form or in the L-stereochemical form. In fact, the D and L stereoisomers of the same monosaccharide can occur in some polysaccharides. When she was working in the chemistry department of the University of Cape Town in 1957, Mavis van Holt showed that D-galactose and L-galactose occur together in one of the seaweed polysaccharides. In their paper in the Journal of the London Chemical Society, Mavis van Holt and John Nunn stated that they'd obtained pure D-galactose and pure L-galactose from the D-L mixture using fractional crystallization. So it's understandable that Mavis van Holt had the reputation of being a top-flight experimentalist. Now, for the benefit of people who are unfamiliar with this type of sugar shorthand, I'll briefly describe what it's all about. If we were to line up two of the molecules of galactose shown and remove the elements of water from the molecule on C1 on the left with a hydroxyl group at C3 on the right and link up the bonds, we'll get a disaccharide where the two D-galactose units are linked by a 1,3-glycosidic bond. Add another galactose to the right and do the same thing. We'll have a trisaccharide with two 1,3-glycosidic bonds. Another one, we'll have a tetrasaccharide with three 1,3-glycosidic bonds. And in this way, we can build up a long chain, which is the main chain of the gum arabic macromolecule. Now, if we put another galactose unit above the main chain and remove the elements of water from the molecule above the chain at C1 with the OH group in the main chain at C6, you'd get a galactose in the branch, and the branch would then be linked to the main chain by a 1,6-glycosidic bond. If we can have branches to the main chain, there's no reason why we shouldn't have branches to the branches, and in gum arabic you do, and these branches, denoted by R in the formula, are the residues L-rhamnopyranose, L-arabofuranose, and the galactopyranose, galactose-arabinose disaccharide. Where these residues are linked to galactose, they're linked by 1,3-glycosidic bonds, but where they link to glucuronic acid, they're linked by 1,4-glycosidic bond. A solution of crude gum arabic would be pH 7. When Fred Smith was working, it was known that the counter ions were potassium, calcium and magnesium. It's now known that there are much smaller quantities of sodium ions and ions of the transition elements, copper, iron and manganese. Fred Smith poured a solution of crude gum arabic acidified with HCl into 5 volumes of ethanol, and the arabic acid precipitated. If you make up a solution of 5% solution of arabic acid, the pH will be about 2. And if that solution is heated on a boiling water bath, you get slow autohydrolysis. After 5 hours, you should be able to pick up the L-arabinose, the L-rhamnose, and the galactose-arabinose disaccharide. After 15 hours, you should pick up galactose, and in order to break the link between the glucuronic acid and the galactose, the solution has to be heated in molar sulfuric acid for 24 hours at 100 degrees centigrade. So the color coding on the slide shows the relative strength of the glycosidic bonds. when you're carrying out acid hydrolysis. The most labile bonds are the ones in green, the most acid resistant in red, and those in between in orange. And now I'd like to point out some unsolved structural features. What are the exact positions of the acid labile residues, denoted by R in this formula, a dash from now on, in the periphery of the gum? For example, what is the acid labile residue in the box shown? Is it L-arabinose, or is it L-rhamnose, or is it the galactose L-arabinose disaccharide? In a review article, Hirst made R prime L-arabinose. That was really just a suggestion. In 1952, I started working on the gum from acacia cyanophylla, which is now called Acacia saligna. Acacia cyanophylla is generally known as the Port Jackson willow. It's also known as Western Australia's golden wattle. During the 1800s, some of these trees, Port Jackson willow trees, were brought into South Africa from Western Australia, and the trees grow extremely well in sandy areas near Cape Town. Acacia cyanophyll trees do not produce vast quantities of gum, but if I went collecting for half a day, I could normally bring back a couple of 100 grams of crude gum, cyanophylla gum. I was much better off than Fred Smith, because in 1945, Partridge, who was working at a low-temperature research lab in Cambridge in England, introduced paper chromatography into carbohydrate chemistry, and 4 years later, Huff, Jones and Wadman, who were working in the chemistry department at the University of Bristol in England, introduced cellulose column chromatography into carbohydrate chemistry. In this day and age, most organic chemists use thin layer chromatography, which is ascending chromatography. If you use paper chromatography, you get much better results if you use descending chromatography. So I needed to get stands made which could fit into my chromatography tanks, which were about 1/2 metre tall. We bought these tanks from the Cape Town post office. At one time, they'd used them for storing sulfuric acid. Now, the stands had to be made so that at the top they could hold troughs which could be filled with solvent mixtures, and one edge of the paper dipped into the solvent and the rest of the paper hung down. All this meant that I had to deal with the most difficult glass blower, and I had to develop monumental patience. Eventually, he made the stands and the troughs. He made me a column for chromatography, and he made me an apparatus which could be filled with liquid stain, and when I connected that to carbon dioxide cylinder, I could spray the stain onto the paper chromatograms. Most people might be completely unimpressed with the fact that I was using what used to be called string and sealing wax science. However, I should like to point out in 1952, Martin and Singh, two British chemists who got the Nobel Prize for introducing paper chromatography into chemistry and biochemistry, ran their paper chromatograms in a drain pipe. I've actually seen a photograph of their apparatus. Over the years, the United Kingdom have had many very imaginative and highly creative scientists. I once visited a university in Basel in Switzerland. The person I spoke to had then recently returned from the United States, where he'd been working in Woodward's laboratory at Harvard. He said to me, "We in Switzerland can do experiments which the Americans wouldn't even try to attempt. But when it comes to imagination, the Americans and particularly the British can beat us hands down." That fella didn't mention Southern Ireland. In 1960, Barry and some other workers in the chemistry department at the university in Dublin were very imaginative. I understand that they had very little money. They did a lot of thinking, mainly in the pubs, and every 10 years or so, they completely revolutionized the area in which they were working. Anyway, once my chromatographic tanks were working, my column was running, I was able to show without too much difficulty that acacia cyanophylla gum was made up of the same monosaccharides that make up gum arabic, but the different monomers were combined in different proportions in the two different polymers. I found that in cyanophylla gum there was a good deal more glucuronic acid than there was in gum arabic, and there was also a good deal more L-rhamnose. The mole ratio of L-rhamnose to D-glucuronic acid was nearly 1:1. I studied Fred Smith's papers and found that in gum arabic the mole ratio of L-rhamnose to D-glucuronic acid was also nearly 1:1, but Fred Smith had made no comment about this. A few years before I did this work, my supervisor, Alistair Stevens, worked out the structure of the gum from Acacia mollissima, which is the black wattle. Alistair also found that the black wattle gum was made up of the same monosaccharides that make up gum arabic, but again the monomers were combined in different proportions in the two different polymers. Alistair Stevens found that in that case there was less glucuronic acid than in gum arabic, and there was also less rhamnose than in gum arabic. But again, the mole ratio of L-rhamnose to L-glucuronic acid was nearly 1:1, and like Fred Smith, Alistair Stevens made no comment about this. The fact that these three different gums had L-rhamnose to D-glucuronic acid in molar ratios 1:1 made me think. At first I thought the results might indicate a significant biochemical connection between D-glucuronic acid and L-rhamnose, but I was unable to write out a pathway linking these two monosaccharides, and I had to give up that line of thought. And then a very simple idea struck me. From the formula, it can be seen here that if you make R prime L-rhamnose for gum arabic and also for acacia cyanophylla gum and also for acacia melissa gum, you can understand why the molar ratios are 1:1 in all three cases. So when I came to write my thesis, I suggested that L-rhamnose was linked to the 4th position of D-glucuronic acid in gum arabic, in acacia cyanophylla gum, and also in acacia melissa gum. I pointed out that E.L. Hirst, one of the leading authorities on carbohydrate chemistry, had come to a different conclusion for gum arabic. He'd made R prime L-arabinose. After my thesis was submitted, we published a paper on acacia cyanophylla gum in the Journal of London Chemical Society, and there we also stated that rhamnose might well be linked to the 4th position of glucuronic acid in gum arabic, in acacia cyanophylla gum, and in acacia melissa gum, and there was a reference to my thesis. In 1959, Fred Smith and Rex Montgomery brought out their monograph on the plant gums and mucilages. And in that book, they also suggested that L-rhamnose was linked to the 4th position of glucuronic acid in gum arabic, and their reason that because the mole ratio of L-rhamnose to D-glucuronic acid was nearly 1:1. In May 1960, I became a fellow at the University Chemistry Department in Edinburgh. When I arrived, Gerald Aspinall told me that I could select my own project and dig my own grave. But when I suggested that I'd like to find out where rhamnose was linked in gum arabic, he immediately told me that that was needle in the haystack research. However, once he'd given me permission to take on a very difficult project, I decided to meet the challenge. Some people might say, look, you're asking a very simple, straightforward question. What's the problem? The problem is that the cognoscenti didn't seem to think that that question could be answered using the methods which were available at the time. Methylation and hydrolysis could not help you. Periodate oxidation could not help you. Therefore, the Barry and Smith degradations could not help you. Okay, what about graded hydrolysis? What I'd really love to get was this fragment here. If I could get that fragment, it's easy to find out what R prime is. But in order to get that fragment, I've got to break the glucuronic acid glycosidic bonds, the red ones. So consider acid hydrolysis. The green bonds are so labile compared to the red that I've got no chance of getting any of the fragment I wanted using acid hydrolysis. The glucuronic acid glycosidic bond becomes labile in sodium hydroxide solution at 160 degrees centigrade under pressure. But if I used alkali at high temperature, anything that came away would be degraded further to give saccharidic acid, and I'd be beaten there as well. A few days after I arrived in Edinburgh, I was talking to Gerald Aspinall, and Professor Hirst walked into the lab. Gerald Aspinall told him what work I wanted to do, and Hirst said, "Do we know what Fred's doing?" That's Fred Smith. And Gerald Aspinall said, "He certainly won't be on this one." You see, at that time, Hirst and other senior members of the British Carbohydrate School tried very hard to make sure that the individual members of the school didn't compete with each other, and Fred Smith and his collaborators were still regarded as part of the British Carbohydrate School. In 2024, the idea of people not competing with each other would be considered weird, but in 1960 it was considered the thing to do. It seemed to me that if I can't do anything with the polymer as it is, what I'd have to do is modify the polymer first. And in particular, I'd have to make sure that the bonds between the glucuronic acid and galactose were made more labile when carrying out acid hydrolysis. If I could convert the red bonds into orange bonds, I'd have an outside chance of getting the fragment I wanted. What could I do? I might be able to decarboxylate the D-glucuronic acids to give D-xylose residues. If I had xylosides, I'd have orange bonds. So using acid hydrolysis, I might be able to get a fragment I wanted. And of course, the acid labile residue would then be linked to xylose. There was a report in the literature that D-glucuronic acid will be decarboxylated in boiling pyridine if you use nickel chloride as a catalyst. But the authors maintained that the reaction will not work if the glucuronic acid is part of a glycoside. And in gum arabic, it is part of a glycoside. Nevertheless, I felt I couldn't sit around indefinitely waiting for inspiration. I had to start somewhere, and this is the place I had to start. So instead of using nickel chloride, I made the nickel salt of the polymer, and instead of using pyridine, I used dimethyl formamide. The reason I used dimethyl formamide was this. It became known during the 1950s that many chemical reactions are markedly speeded up if you carry them out in polyprotic solvents, and it became fashionable to use them. What I found was that the D-glucuronic acids did not decarboxylate, but there was degradation in the reaction. I could see that because a good deal of caramel had formed. One possibility was that the caramel had formed because the dimethyl formamide has a boiling point of 153 degrees centigrade. If that was indeed the case, I could argue that you should get a similar degradation in water at 150 degrees under pressure. If you work in water, you don't get caramel formed, and you could learn something about this degradation. I was talking about that, and David Manners, who was a lecturer at Edinburgh at the time, pointed out to me that a few months before I came to Edinburgh, one of Gerald Aspinall's students had found a most unusual autohydrolysis in the fructosane series. I spoke to Gerald Aspinall and he said, yes, they took a solution of the fructosane, which was pH 7, heated it up, a small amount of lactic acid formed, which was able to catalyze a very, very slow autohydrolysis. If they first put the fructosane into a buffer at pH 7, they did not get this autohydrolysis. After I heard all that, I realized that there was a completely different approach to this problem that I was trying to solve. In the fructosane, the fructose units are in the furanose form. In my case, the arabinose and the arabinose part of the disaccharide were in the furanose form, but the rhamnose was in part of the pyranose form. So if I could get the Gerald Aspinall type of autohydrolysis, I might be able to find conditions to remove the arabinose and the galactose arabinose disaccharide and leave the rhamnose as part of the polymer. Then by methylation and hydrolysis, I could find out if it was linked to galactose or glucuronic acid. So the first experiment I did was to take some of the nickel salt of the glucuronic acid, dissolved it in water, took about 0.5 milliliter into a thin Pyrex tube, sealed the tube and heated the solution in an oil bath for 8 hours a day over a period of 5 days. I cooled the solution down well, cut the top of the test tube and examined the solution by paper chromatography and found that there'd been considerable hydrolysis. And the reason was that the pH was 5 and at the high temperature the hydrolysis decided to get going. So then I made the barium salt. Using a solution of the barium salt, which was pH 7, I soon found I could get the Gerald Aspinall type of autohydrolysis. And when I first dissolved the barium salt in the buffer at pH 7, I did not get this hydrolysis. So then it was a case of different temperatures for different lengths of time at different concentrations. While I was doing this work, the late J.K. Innes Jones happened to be visiting Edinburgh. Jones, I think, left the University of Bristol in 1953 to become a professor in Ontario in Canada, and a few years after in Canada, he was made a Fellow of the Royal Society of London. Soon after he came into the department, Professor Hirst brought him to speak to me. And Jones was really very interested in this possibility of removing the rhamnose and the disaccharide and leaving rhamnose as part of the polymer. I expect if I could make something like this work, he and the other polysaccharide chemists could use my results when they were dealing with polymers containing methyl pentoses. So when I was working at temperatures below 100, I'd use conventional flask condensers, and temperatures above 100, I'd use sealed tube reactions. After every reaction, I'd either examine the tube or the flask by paper chromatography. And every time I found that when I got a arabinose, I also got rhamnose. So eventually, despite the encouragement I got from Ken Jones, I decided to give up this approach and go back to try to modify the polymer. I expect if I did one more experiment, it would have worked. That experiment was never done. I'd also like to note that I wasn't doing exact analytical work because I wanted this to be all or nothing. Otherwise, if I carried out methylation and hydrolysis on the graded polymer, I'd get ambiguous results. Okay, instead of trying to decarboxylate the glucuronic acid residues, I might be able to reduce them to glucose residues. All chemists know that if you want to reduce the carboxyl group in benzoic acid to give benzyl alcohol, you use lithium aluminium hydride in dry diethyl ether or dry tetrahydrofuran. But these polymers are insoluble in diethyl ether or tetrahydrofuran or any other ether solvents. Okay, acetylate the free hydroxyl groups in the polymer. In 1945, Carson and McLean, the United States, showed how this can be done. The polymer is dissolved in formamide and then react with acetic anhydride and pyridine. And now you've got the acetylated polymer, which is soluble in diglyme, which is an ether solvent. You could use lithium aluminium hydride reduction. No. The reason why this won't work is because acetates are esters, and lithium aluminium hydride will reduce esters faster than carboxyl groups. So as soon as some of the acetyl groups are removed, the polymer falls out of solution and the carboxyl groups remain unchanged. In 1955, Alistair Stephen was working in the chemistry department of the University of Edinburgh, having gained sabbatical leave from Cape Town University. He was working in the same laboratory as a Swiss fellow called George Zweifel. At the end of this year in Edinburgh, Stephen went back to Cape Town. Zweifel stayed on in Edinburgh for a year, and then he went to work with H.C. Brown at a university in Chicago in the United States. 20 years later, H.C. Brown got a Nobel Prize for chemistry. In 1959, Alistair Stephen again got sabbatical leave, and this time he went to work with Fred Smith in Minnesota. Soon after he got to the States, he passed through Chicago and saw Zweifel, and Zweifel told him that they were investigating the reducing properties of diborane, and the diborane could reduce carboxyl groups faster than ester groups. And Zweifel pointed out to Stephen that this could be a way of reducing carboxyl groups in acid polysaccharides. Stephen told Fred Smith about this, and then early in 1960, Stephen and Smith published a paper in Tetrahedron Letters saying that they'd reacted acetylated gum tragacanth with diborane in diglyme, and after removing the acetyl groups, produced carboxyl-reduced gum tragacanth in good yield. In 1959, Gerald Aspinall was also in the States on a lecture tour, and he saw Zweifel also. And then when he went back to Edinburgh, he told one of his students to acetylate one of the hemicelluloses and reduce the carboxyl groups with diborane. These compounds are similar to the gums in that they have a long chain, this time xylose, and they have side chains ending in uronic acid, 4-O-methylglucuronic acid. When the student tried out the reaction, he found that the carboxyl groups were not reduced. Okay, if you want to do a diborane reaction, this is what you could do. You could connect up two flasks, A and B. In flask B, you have a solution of the acetylated polymer in diglyme. That's where you want the reaction to take place. In flask A, you have a solution of sodium borohydride in diglyme. At the top of flask A, you have a Y piece. Connected to the top of the Y, you have a separating funnel containing borotrifluoride in ether, and the other arm you have an ordinary tube which connected to a nitrogen cylinder. All the connecting tubes, all the glassware, and all the chemicals have to be perfectly dry. And at the end of the apparatus, you have a guard tube containing calcium chloride or silica gel to prevent moisture coming in from the atmosphere. You then open the tap of the separating funnel and let the boron trifluoride in ether drip into flask A. When it comes into contact with the sodium borohydride, it reacts to form diborane gas, and then you open the valve of the nitrogen cylinder and get the diborane to go from flask A into flask B. There's another method of doing this. In the second method, you dissolve both the polysaccharide acetate and the sodium borohydride in a conical flask. You add a small quantity of the boron trifluoride in ether, fit a rubber bug, and swirl the contents of the flask. When this gas subsides, you keep adding another quantity until you've added the lot. In this day and age, it's possible to buy a solution of borane in THF from the Sigma Aldrich company in the United States. I've seen in the literature that about 10 years ago, the Sigma Aldrich company was taken over by the Merck Group in Darmstadt in Germany for a price of $17 billion. I think this is interesting because before the Second World War, the Merck Group had a subsidiary in Rahway, New Jersey in the United States. But when USA got into the Second World War, they confiscated all German companies in the USA, and after the war, Merck remained American. And now the Germans have bought back one of the big American companies. Anyway, at the time I discussed this with Gerald Aspinall, and he persuaded me to use the first method because all the ions that were produced in the reaction remained in flask A, and you didn't have to get rid of them at the end. So I tried this out, and what I found was soon after the diborane got into flask B, the mixture set to a gel, and the carboxyl groups were not reduced. And that was exactly the same thing that Fanshawe had found when he tried to reduce the carboxyl groups in his hemicellulose. I think Gerald Aspinall was pleased with my result because when his student could not get the reaction to work, he found that some other people couldn't do it either. But Stephen and Smith had used the second method, so I had to try that. And I found that after about the third addition of the boron trifluoride, the mixture in the flask became a solid. So then I put the rubber bug in properly, shook the flask well, the gel broke, gas started coming off again, and then the reaction worked well. At the end of the reaction, I decomposed the reaction mixture with water, distilled off the diglyme, removed the acetyl groups by saponification, removed the ions by dialysis, and poured the dialyzed mixture into 5 volumes of ethanol, and the carboxyl reduced cum arabic precipitated in good yield. A few years after I left Edinburgh, I got a letter from Gerald Aspinall saying that they'd managed to make the first method work as well. They had to leave the mixture for some 3 weeks under diborane pressure. Now I had the reduced polymer, I had to see what I could do with it. So I tried acid hydrolysis. And using acid hydrolysis, I could not find any unusual oligosaccharides using paper chromatography, and that was a blow, but it wasn't a knockout blow. If a person were to take a sharp knife and cut it into the stem of an acacia tree and come back a few days later, you might find that the hole is filled with gum. And the general view is that the gum forms to protect the tree from attack by microorganisms. So therefore it's understandable that the view is that the gum will not be attacked by enzymes from microorganism, and you won't get hydrolysis. But now I've modified the gum, I might get enzyme-promoted hydrolysis. So I tried a number of commercially available enzymes. There was no hydrolysis. Some people in Manners' lab in Edinburgh University were growing molds in polysaccharide solutions. They would then extract the hydrolytic enzymes from these molds and use those enzymes to promote the hydrolysis of the original polysaccharide. One of these people decided they will try this out for me. So I gave them a solution of the original polymer and a solution of the reduced polymer. The molds did not grow in the solution of the original polymer, and they didn't grow in the solution of the reduced polymer either. Okay, if all the obvious things fail, the only thing a person can do is sit back and do some thinking. So I asked myself, what is rhamnose? Rhamnose is 6-deoxy-L-mannose. What I was hoping to get was a polymer consisting of glucose and rhamnose. Instead of thinking glucose and rhamnose, think glucose and mannose. Once you do that, you realize that there's a whole polymer series of glucomannans. So I studied the literature on glucomannans and found that a few years before, Fred Smith and Srivastava had submitted one of these glucomannans to acetolysis. What they did was they added acetic anhydride and a few drops of concentrated sulfuric acid to the glucomannan and then let that sit overnight. They decomposed the reaction mixture with water and then extracted the mixture of acetates into chloroform. The chloroform was removed by distillation and the acetyl groups were removed in methanol solution using a small amount of sodium methylate according to the Zemplay procedure. From the deacetylated mixture, they isolated a disaccharide made of glucose and mannose. I had to try deacetylation. I had 200 milligrams of the reduced polymer and used the acetylated and deacetylated mixtures shown by Fred Smith and Srivastava. At the end of the reaction, I decomposed the mixture with water and ran a paper chromatogram and showed that all 4 monosaccharides were present. And indeed, there must have been at least 10 new spots on paper chromatograms as compared with acid hydrolysis. I couldn't tell anything from that. So I got the glass blower to build me a small glass column about 10 centimeters long and 2.5 centimeters in diameter. As glass blowers glow, that glass blower in the chemistry department in Edinburgh was most unusual. He was helpful. Anyway, I packed the column with a mixture of charcoal and sealite. It was a standard mechanism in those days. I then ran the mixture into the charcoal and cellulose and ran water down through the column until I could not detect any monosaccharides coming off. I then used water containing 0.5% of ethanol, 1% of ethanol, 1.5% of ethanol, 2%, and so on. I concentrated all these fractions to 2 milliliters. I then examined them first by paper chromatography to show that there were no monosaccharides. I then hydrolyzed each of these fractions, adding 3 mils of half molar sulfuric acid and refluxed for 8 hours on a boiling water bath. The solutions were cooled and the sulfuric acid was neutralized with solid barium carbonate. The excess barium carbonate and barium sulfate were removed by precipitation, and I examined the filtrates by paper chromatography. In the filtrate from the 1.5% ethanol, I picked up rhamnose after hydrolysis. As far as I was concerned, that rhamnose must have come from the hydrolysis of a rhamnose containing oligosaccharide, and that was the breakthrough I was looking for. But Gerald Aspinall and some of the other people in Edinburgh were not convinced. A few days after I'd got this result, I was in London and went to the Lister Institute and spoke to Bill Whelan, who was regarded as one of England's top polysaccharide chemists. And he told me the job could not be done, particularly by the approach which I'd been using. These people were not idiots. They had every right to be skeptical of my interpretation of the acetylosis results. See, if I'd mentioned that some of the monosaccharides were still present after the acetylosis, assuming that some of the rhamnose might not have been deacetylated, it would have stuck to the charcoal, removed with the 1.5% of ethanol, and then when hydrolysis of sulfuric acid, you would have picked up rhamnose after the hydrolysis. But I had so much confidence in my interpretation of the acetylosis that when I got back to Edinburgh from London, I decided to try and make 10 grams of the reduced polymer. And then I carried out the acetylation and the acetylosis and deacetylation. I then used first cellulose column chromatography, then charcoal sealite column chromatography, and cellulose column chromatography again. And at the end of that, which took well over a year, I got a gram of syrupy oligosaccharide which contained rhamnose and showed only one spot on the paper chromatogram. I'd like to note here that cellulose column chromatography is very different from column chromatography using silico-alumina. If you use silico-alumina, you're using adsorption chromatography. If you use cellulose chromatography, you're using partition chromatography. So it's possible to use the same cellulose column for months on end, and you could switch it off every night. Using cellulose column chromatography, it's often possible to separate substances which are very similar chemical and physical properties. In this day and age, of course, you could use high-performance liquid chromatography, which is much faster. In my case, not only was the chromatography slow, but it was tricky because I didn't know which spot on paper corresponded to the material I was looking for. And I was using paper chromatography to follow the fractionation on the columns. So what I did was this. After removing all the monosaccharides and any material that had not been fully deacetylated from the first cellulose column, I hydrolyzed small quantities of every single fraction to find out where the rhamnose was going. And then by a process of elimination, I found out what I was looking for. Once I knew which spot corresponded I'm looking for, I could combine all those fractions, remove the solvent by distillation, took up the residue in water, and then used the charcoal sealite column to separate disaccharides from higher oligosaccharides, and then used the second cellulose column to separate the disaccharides. What I did was I reacted 100 milligrams of the syrup with phenylhydrazine acetate to form a solid phenylosazone. This is a well-known reaction which Emil Fischer discovered in the 1870s. Microanalyses for carbon, hydrogen and nitrogen on the phenylosazone, or elemental analyses as it's called these days, was carried out at the University of Oxford, and the percentages found were in good agreement which I'd calculated for a disaccharide made up of a hexose and methyl pentose. I then hydrolyzed some of the phenylosazone and ran a paper chromatogram. The only monosaccharide I could pick up with a pyranizidine in butanol spray reagent was L-rhamnose, and that told me that rhamnose was the non-reducing end of this disaccharide, and that was very good. I then also hydrolyzed the syrup and picked up rhamnose and glucose, and then Gerald Aspinall and the other people at Edinburgh were convinced, and they felt that the problem had been solved. But then I got difficult. I wasn't too happy with the fact that I just used the paper chromatography to decide that I'd had glucose, even although it's well known that you could separate glucose and galactose. So what I decided to do was to see if I could characterize the glucose. The obvious thing at that time was to hydrolyze the disaccharide, remove the rhamnose, and then characterize the hexose. But it's an odd thing, if you're working on the 50 milligram scale, it's often very difficult to get the glucose to crystallize. So this is what I came up with. If we consider the disaccharide, rhamnose is linked to glucose, and first reduce that and then hydrolyze that, you'd get rhamnose and a glycetol. Now then, if you were to then make the solution alkaline, strongly alkaline, and heat it up, the rhamnose will be converted into saccharidic acid, which can be removed by ion exchange resins, and you'd be left with a glycetol. So working on the 100 milligram scale, I reduced the disaccharide with sodium borohydride and then hydrolyzed the solution with sulfuric acid. Instead of using strong alkali like potassium hydroxide, I used an excess of strong base resin in the amberlite IR400 in the OH form. The first thing that would happen is the OH would exchange with the sulfuric, and I'd remove the sulfuric acid. Then by heating it up, heating the solution, I'd get a similar result to using potassium hydroxide and get the rhamnose converted into saccharidic acid, and once the saccharidic anion is formed, it would exchange with the OH on the resin, so that would be removed as well. So then I just filtered off the solid glycetol, and it was amorphous, and then I acetylated it with acetic anhydride, produced a nicely crystalline hexaacetate, which I showed to be identical with the hexaacetate which I'd made from authentic glucetol or sorbitol, as it's more known. So the monosaccharide was glucose. Okay, so rhamnose is linked to glucose, and I've numbered the glucose from the CHO down. I knew that the rhamnose was not linked to positions 1 and 2 because the disaccharide had formed an osazone. I reacted 10 milligrams of the syrup with lead tetraacetate in 98% acetic acid, and after removing the lead and hydrolyzing, I picked up rhamnose and erythrose on a paper chromatogram. From work I did in Canada, I knew that this eliminated position 3, because if it been position 3, I should have got rhamnose and arabinose. So that left positions 4, 5, and 6. If you oxidize with periodate and the position is 4, you'd get formaldehyde from the CH2OH at the end of the chain. But if it's 5 or 6, you don't get formaldehyde. Using periodate oxidation, I produced formaldehyde diamidone complex in good yield. Since I was working in Edinburgh, I decided to see if I get further evidence from the methylation and hydrolysis method which had been introduced by Howarth and Hirst. If the rhamnose is linked to glucose by a 1,4 link, you would get the formula shown. And if you methylate that and then carry out the hydrolysis, you'd break the bond between the two rings and you'd remove the methyl group at the end of the right-hand molecule. I methylated a few hundred milligrams of the disaccharide with dimethyl sulfate and sodium hydroxide, which is the Howarth method. The disaccharide wasn't fully methylated, so I dissolved the partially method in methyl iodide, added silver oxide and heated for several hours under reflux. That's the Purdy method. And the molecule was still not fully methylated. So then I used Nobel laureate Richard Kuhn's modification of the Purdy method, where you dissolve the partially methylated disaccharide in dimethyl sulfoxide. You add the methyl iodide and the silver oxide and stir for 24 hours at ambient temperature. And then my product was fully methylated. I'd like to mention here that in the labs at Macquarie University, both the student labs and also the research labs, there are plastic gloves of different sizes. At Edinburgh University, there were no plastic gloves. I don't think they were invented at that time, and they certainly didn't give us the latex gloves that were used by the surgeons. Now, dimethyl sulfite is supposed to be very poisonous and can go through the skin. So we used to do the methylations in the fume cupboard with a beaker of very strong sodium ammonium hydroxide solution and some cotton wool. So if you got any of the dimethyl sulfite on your skin, you'd put the cotton wool into the ammonium hydroxide and immediately put it onto your skin to neutralize the dimethyl sulfate. A few months before I was doing this work, Gerald Aspinall got apparatus to do gas chromatography. So before doing the acid hydrolysis, I reacted a couple of milligrams with methanol hydrochloride in a sealed tube, heated for a number of hours, and then cooled it down and gave the tube to Gerald Aspinall. He injected some of the material into the gas chromatogram and told me that he'd produced the methyl glycosides of 2,3,4-trimethyl-rhamnose and 2,3,6-tri-O-methyl glucose. I then hydrolyzed the product with sulfuric acid, removed the sulfuric acid with barium carbonate, and separated the trimethyl compounds on the cellulose column. I characterized the trimethyl-rhamnose as the analyte and showed that it was identical with the authentic sample which I scrounged from one of the Elizabeth Percival's research students. And the tri-O-methyl glucose was characterized as a dibenzoate, which compared with an authentic sample. So the link was 1,4. When I started, I knew that there was an acid labile residue linked to glucuronic acid. So if the glucuronic acid residues were reduced, you would expect the acid labile residues to be linked to glucose. Now, if the acid labile residue is rhamnose, and you can get a disaccharide which is made up of rhamnose and glucose, then you can see that the link is 1,4 and everything fits. We did one more thing though. One of Gerald Aspinall's students methylated the polymer completely and carried out a methanolysis, and Gerald Aspinall showed that using gas chromatography, that there was 2,3,4-triomethyl rhamnose, which showed that rhamnose was an N group, and he showed also that you got the methyl glycoside of the methyl ester of 2,3-dimethyl glucuronic acid that showed that glucuronic acid had a residue at position 4, and those results fitted perfectly with Fred Smith's old work. So then we were able to publish a paper in the Journal of the London Chemical Society. I was pleased that Professor Hirst was prepared to put his name on that paper. He was not at all upset that this relatively young person, I was 31 at the time, had come over and disproved one of his suggestions. When he was young, he disproved some of the suggestions of Emil Fischer, and very few people have managed to correct any of the writings of Emil Fischer. Using the internet, I found a list of possibly the 100 best scientists of all time. Emil Fischer's name was on that list. Earlier in this talk, I suggested that there may be a biosynthetic connection between D-glucuronic acid and L-rhamnose. On the basis of modern knowledge of the biosynthesis of D-glucuronic acid, on the biosynthesis of L-rhamnose, on the biosynthesis of D-galacturic acid, and on the biosynthesis of polysaccharides, I'd like to show that there could well be a biosynthetic connection between D-glucuronic acid, D-galacturic acid, and L-rhamnose. All chemists know about ATP, adenosine triphosphate, but you can also get nucleotide diphosphates. And one of these nucleotide, uridine diphosphate, can link up with glucose to give uridine diphosphate glucose, which can be written as UDPG. Then the presence of an enzyme galactowaldinase, you could get an equilibrium mixture of uridine diphosphate glucose and uridine diphosphate galactose. There are enzymes in mung beans which can cause the oxidation of these to give you uridine diphosphate glucuronic acid and uridine diphosphate galacturonic acid. Another nucleotide is thymidine diphosphate glucose. In the presence of a number of different enzymes, thymidine diphosphate glucose can be converted into thymidine diphosphate L-rhamnose. So starting with glucose, you could get nucleotides which contain D-glucuronic acid, D-galacturonic acid, and L-rhamnose. There are also enzymes known as the glycoside transferases, which can transfer the sugar part of a nucleoside to react with another monosaccharide. So if you were to take uridine diphosphate glucose and fructose in solution and add the correct transferase, you would get the glucose removed from the nucleoside to react with fructose to give sucrose. And sucrose has been made in this way. But these glycoside transferases can not only transfer monosaccharides to another monosaccharide, it can transfer it to another oligosaccharide, and this can happen over and over again, and this is the way in which polysaccharides are biosynthesized. So starting with glucose, we can get nucleosides which contain D-glucuronic acid, D-galacturonic acid, and L-rhamnose. So therefore, in the presence of the correct transferases, you would expect to get polysaccharides which contain D-glucuronic acid and D-galacturonic acid if there is a biochemical connection between these two. And this is what you do find. Then if there's a biochemical connection between D-glucuronic acid and L-rhamnose, you'd expect to get polysaccharides which contain D-glucuronic acid and L-rhamnose, and that's what you find. Now, if you think that there could be a biosynthetic connection between D-galacturic acid and L-rhamnose, you'd expect to find polysaccharides which contain D-galacturic acid and rhamnose, and you do. What about polysaccharides which contain all three? Glucuronic, I don't know of any, but I think they could well be found. But even if one of these is found, or one is known and I don't know about it, it will still be necessary to find an experimental method to demonstrate that the biosyntheses of D-glucuronic acid, D-galacturic acid, and L-rhamnose are in fact connected. In 1963, I was back working in the chemistry department at the University of Cape Town, and I thought I'd reinvestigate the gum from acacia cyanophylla and try out the method which I developed in Edinburgh. Because the acacia cyanophylla gum was much more acidic than gum arabic, I found that the diborane reaction only gave 50% reduction. However, in the original paper, Stephen and Smith stated that if you have problems, instead of starting with the acetate, start with the propionate. So I made the propionate and found that reduction gave me 90% reduction. I also found that in the acetylysis, I found better results if I first acetylated the reduced polymer. And then everything went smoothly. I found the exact same disaccharide which I'd found in Edinburgh, and that was the result I expected to find, and I decided not to publish the work. However, in 1973, Bengt Lindberg showed that one of the bacterial polysaccharides contained rhamnose linked to the 4 position of glucuronic acid. Lindberg's method was completely different from the method which I had used. Lindberg first fully methylated the bacterial polysaccharide. Now take a look at the formula. It can be seen that the O prime is linked not only to the 4 position of the glucuronic acid, but it's also in the beta position to the methyl ester group. And when esters like that are treated with very strong alkali, you get a beta elimination reaction and the OR prime leaves. Lindberg used sodium methoxide for 15 minutes at room temperature. He first analyzed the polymer before reacting with the sodium methoxide, and he also analyzed the product after reacting with sodium methoxide. By comparing the two different results, he could see which residue had been lost. Using this alkaline method, elimination method, Lindberg and his associates, and also some other groups, showed that rhamnose was linked to the 4 position of glucuronic acid in several of these different bacterial polysaccharides. And those results stimulated Fugedi in Hungary to try and synthesize the disaccharide where L-rhamnose was linked to the 4 position of D-glucuronic acid. Fugedi published the synthesis in 1987. He first synthesized the disaccharide where rhamnose was linked to the 4 position of glucose, and all the hydroxyl groups were protected with the exception of the hydroxymethyl group, the CH2OH group of the glucose. He oxidized the CH2OH to carboxyl and removed the protecting groups, and that gave him his final product. In this day and age, many synthetic organic chemists avoid the use of protecting groups, but I think that protecting groups are still of some value in certain areas of organic chemistry. A few years after Fugedi's paper appeared in the literature, I got a letter from the editor of the Canadian Journal of Chemistry. He said that Canadian Journal of Chemistry editorial board wanted to celebrate McGill University's Professor Arthur Perlin's 67th birthday by dedicating one of their monthly issues to Arthur Perlin. The editor invited me to send a paper to the special issue, and he said all papers will be refereed by two different referees in the usual manner. In 1950, Arthur Perlin was working for the Canadian Research Organisation in Ottawa, which is similar to the CSIRO here. He got sabbatical leave and spent a year working with Professor Hirst in Edinburgh. Hirst and Perlin worked on the polysaccharide from Acacia pycnantha, which is indigenous to South Australia. So I thought it would be appropriate for me to write up my own work on acacia cyanophylla gum and send that to the editor of the Canadian Journal. I wrote a paper and sent a copy of that to Alistair Stephen because I was mixed up in the work with him. I suggested that he may like to be a co-author. He wrote back saying yes, he would accept my offer of being a co-author for two reasons. One, he wanted to join me in the special tribute to Arthur Perlin, and secondly, could make a contribution. One of his students, Neil Ravenscroft, had made a detailed NMR study of the disaccharide where L-rhamnose was linked to the 4 position of D-glucose. Ravenscroft confirmed the structure which I'd worked out by classical methods. In fact, he studied a disaccharide which I'd left in Cape Town 20 years before. Alistair Stephen wanted to include this work in the paper, and he asked me if I'd prepared to let Ravenscroft's name go onto the paper. Of course, I agreed to that. Ravenscroft was very pleased about this because he was going to do postdoctoral work in Canada, and if he had his name on a paper in the special issue, it would be of advantage to him. Anyway, in that special paper, I pointed out that you get the same structural feature in a number of bacterial polysaccharides and in 2 different gums. And I suggested in the biosynthesis of the plant polysaccharides, there may be a step where rhamnose from a bacterial nucleoside, diphosphate rhamnose, is transferred to the plant polysaccharide using a bacterial nucleoside transferase. In other words, a combined bacterial plant biosynthesis at the molecular level. Even although it's very well known that some bacteria can fix nitrogen and the ammonia produced can be used by plants, I thought the idea that I was putting forward might be considered way out. So I was pleased that the referees did not challenge it. I should note, though, that in one of his NMR works, Ravenscroft used a Russian method to confirm the absolute configurations of D-glucose and L-rhamnose. One of the referees challenged that, but Alistair Stephen was able to convince the referees that the Russian method was sound, and the paper was accepted. After the paper was accepted, I read Richard Dawkins' book on the ancestor's tale. In that book, Dawkins maintained that many years ago, bacteria played the role in plant cells which mitochondria play now. If that is indeed the case, then the idea of a combined bacterial plant biosynthesis is not way out at all. Hopefully, in the not-too-distant future, somebody might find an experimental method to test whether this idea of a combined bacterial plant biosynthesis is true or false. After the paper was accepted, I again started thinking about gum arabic. By taking into account some new experimental method about the structure of gum arabic and some educated guessing, I came up with this formula for gum arabic. I sent a copy of that to Alistair Stephen in Cape Town, and he said he was thinking along similar lines. A few years later, Alistair Stephen and Shirley Sherms gave a formula for gum arabic in a monograph on food polysaccharides. Shirley and Alistair and various other people like to use that type of diagram to depict the primary structure of these heteropolysaccharides. In 2000, I got an unexpected phone call from a very old friend, Phil Gorin. Phil Gorin is an Englishman who got his PhD at the University of Bristol, and he spent many years working in the Prairie Regional Research Laboratory in Saskatoon in Canada. Over the phone, Phil told me that the director of the Prairie Regional Lab told him what research he had to do. He wasn't prepared to accept that, and he got himself a lectureship at a university in Curitiba in Brazil. I gave Phil my email address, and we started corresponding using the email. Phil told me that he'd always avoided working on these plant gums because he thought they were too complicated. But once he got to Brazil, he started working on the gums from one of the Brazilian trees, which the Aztecs had used in some of their medicines. And he was also working on gum arabic. When Phil was still working in Bristol, one of the people showed that in addition to the polymer, there were very, very small amounts of the monosaccharides that make up the polymer. Phil has found that in addition to that, there are very small amounts of oligosaccharides. So him and his fellow workers in Curitiba have been isolating these oligosaccharides and up to heptasaccharides and working out their structures using NMR. In Edinburgh, Gerald Aspinall once told me that Hirst maintained that these gums can be slowly hydrolyzed in the solid state. I pointed this out to Phil and asked him if his oligosaccharides were formed in this way. He said that was possible, but the significance of his work was that these oligosaccharide structures should be directly related to the polymer itself, and there was evidence for that. As early as 1931, Challoner, Howarth and Hirst showed that when galactose was linked to, when glucuronic acid was linked to galactose in gum arabic, the links were 1,6. In Phil Gorin's oligosaccharides, when glucuronic acid is linked to galactose, the links are 1,6. Fred Smith showed that when galactose is linked to galactose, the links are 1,3 and 1,6. In Phil's oligosaccharides, galactose is linked to galactose by 1,3 and 1,6 linkages. Fred Smith also showed that when galactose was linked to L-rhamnose in gum arabic, the links were 1,3. In Phil's oligosaccharides, when galactose is linked to L-rhamnose, the links are 1,3. And in Phil's oligosaccharides, rhamnose is linked to the 4th position of glucuronic acid. What he's done is introduce a novel method of gaining information of the primary structure of these heteropolysaccharides. So I sent him a copy. He also asked for the reference of the work by Alistair Stephen and Shirley Sherms, which recognized my help. A later email, Phil told me that he'd had a paper accepted for publication on gum arabic, which he'd submitted before he'd been corresponding with me. He said the abstract and said, you can see that the work is in agreement with some of your ideas. And he also said that his work was well accepted. I'm not surprised that Phil's work was well accepted, and I'm pleased that he's experimental work agrees with some of my ideas. But I must emphasize that Phil's method is an indirect method because he hasn't worked on the polymer itself. Indirect methods have been used by other scientists. For example, in determining the age of dinosaur bones, it was not possible to do carbon dating on the bones themselves, so they dated the stones around the bones. I'm not sure which isotopes were used. In the present case, it would be great if a direct method can be used to see if the indirect methods that Phil has used can be confirmed. Phil did actually record the NMR spectra of the polymer itself, but he was not able to use those spectra to gain information about the fine structure. That's why he concentrated on the oligosaccharides. Okay, and now I would like to just point out a paragraph which I've taken from an article which was written in memory of the late Sir Edmund Hirst. It can be seen there that my name is mentioned. I was pleased that my name was mentioned in this article because I had a high regard for Sir Edmund. Hirst was not a Nobel laureate, but some people at Edinburgh maintain that the Swedish Academy should have invited him to share the prize with Sir Norman Haworth, and certainly Hirst was a big name in chemistry for a very long time. When I was in Edinburgh, Gerald Aspinall was senior lecturer. He left Edinburgh in 1970 to become a professor at a university in Toronto in Canada. While he was in Canada, he was awarded the Hudson Prize by the American Chemical Society. Early in 2007, I phoned Alistair Stephen in Cape Town. He told me that Gerald Aspinall had just soon passed away. So I sent an email to Phil Gorin in Brazil. Phil emailed back that he'd heard Gerald Aspinall had died of a long illness. Phil was not directly associated with Gerald Aspinall, but he worked with J.K. and Jones, who was associated with Haworth and Hirst. Some areas of science are almost like a family. Okay, there we could see a picture of the Edinburgh Castle. There's a picture of Table Mountain. This is a good picture. I've got it from the travel section of Sydney Morning Herald. I would like to have shown a picture of the Table Mountain covered by the tablecloth, but unfortunately I could not find a good picture. Before concluding this talk, I would just like to say that I'd like to dedicate the lecture to memory of my late wife, Alec Charlson, who spent several years working as an examination supervisor at Macquarie University. In conclusion, I want to give my email address, which is Alec, A-L-E-C, .Charlson, C-H-A-R-L-S-O-N, @gmail.com.